Right now, somewhere out there, two black holes are circling each other. Not the ordinary kind, not the ones that form when a star dies. These things contain more mass than 4 billion suns, each one, and they've been doing this for over 100 million years, slowly tightening, closing the gap by fractions of a percent per million years. The universe is not in a hurry, but when they finally touch, and they will, the gravitational energy released in that single moment will outstrip every star in the Milky Way, burning at full intensity for 10,000 years. All of it gone in 1 second. The terrifying part, we've already felt the shockwave from events like this. We just didn't have a name for what we were sensing. Here's something it took astronomers most of the 20th century to accept. At the center of nearly every large galaxy, every single one, there is a supermassive black hole. Not a regular black hole. Those form when stars die, and they typically weigh between 5 and 50 times what our sun weighs. Compact, violent, but on a cosmic scale, small. Supermassive black holes are something else entirely. The one at the center of our own galaxy, Sagittarius A star, you've probably heard the name, weighs about 4 million solar masses, 4 million suns compressed into a region smaller than our solar system. It sits roughly 26,000 light years from Earth, and for decades, astronomers could only infer it was there by watching nearby stars move. Those stars behaved like they were orbiting a drain that nothing could explain. In 2022, the Event Horizon Telescope finally imaged it. That fuzzy orange ring didn't come from a single camera. It was assembled from data collected simultaneously by radio observatories across the entire planet, Hawaii, Chile, the South Pole, all synchronized to within a fraction of a nanosecond. The result, one image, the shadow of a black hole. 4 million solar masses. And that doesn't even get you into the top tier. M87, the galaxy Messier 87, sitting about 53 million light years away, has a black hole at its center that weighs 6.5 billion solar masses. Not million, billion. If you placed it where our sun is, its event horizon would extend past the orbit of Uranus. And M87 isn't even close to the record. TOEN 618 is a quasar from when the universe was young, an ancient feeding black hole, and it carries 66 billion solar masses. Its event horizon is 10 times larger than our entire solar system. These are the scales we're talking about. These are the objects that, under the right conditions, find each other. So how does that actually happen? Galaxies collide. Not as some rare exception, not metaphorically. It's just what galaxies do, one of the primary ways the universe builds larger and larger structures. The Milky Way has been absorbing smaller dwarf galaxies for billions of years. We can still trace their remains in the orbits of certain star clusters, in streams of stars, following ancient paths around our galaxy's disk, ghost signatures of things we swallowed long ago. In roughly 4 billion years, Andromeda hits us. It's already incoming at about 110 kilometers per second. We've tracked its trajectory. We know, more or less, what happens. Most stars survive. The two galaxies pass through each other, pull apart, fall back together, and eventually settle into a single elliptical galaxy over about 6 billion years. And somewhere in that process, two supermassive black holes, ours and Andromeda's, which likely outweighs ours by around 25 to 1, begin a very long approach toward each other. Here's the thing about galaxy collisions that always trips people up. Galaxies are almost entirely empty space. When two of them collide, individual stars almost never physically hit each other. The distances between them are just too vast. It's less like a crash and more like two enormous, loosely scattered clouds of particles drifting through one another. Gas and dust are a different story. When gas clouds ram together, they compress, heat up, and trigger massive bursts of star formation. The antennae galaxies, two spirals currently mid-merger, about 45 million light-years away, contain dozens of enormous star-forming regions, each producing thousands of new stars that wouldn't exist without the collision. And at the center of all that chaos, two supermassive black holes start pulling toward each other. At first, they're separated by tens of thousands of light-years. They orbit the combined center of mass, gradually losing energy through a process called dynamical friction, not by directly interacting, but by gravitationally dragging on surrounding stars and gas, plowing through the galaxy like ships through water, leaving wakes, slowly spiraling inward. This is slow, hundreds of millions of years, sometimes billions. The universe isn't rushed. Eventually, the separation drops from thousands of light years to hundreds, then tens, and then something unexpected happens. It stops. One parsec is about 3.26 light years. 3 light years. By galactic standards, that's almost nothing. But for two supermassive black holes trying to merge, that last parsec has been one of the most stubborn problems in theoretical astrophysics for over 40 years. It's called the final parsec problem. Here's why it matters. As the two black holes spiral inward through the surrounding galaxy, they shed energy by scattering stars. Every time a star passes close to the binary, it gets slingshot away at enormous speed, carrying a small slice of orbital energy with it. When there are plenty of stars in the right orbits, this is efficient. It works. But eventually the supply runs dry. The black holes have ejected or swallowed every star in a useful orbit. The friction drops to almost nothing, and the pair just circles, stuck at roughly 1 parsec, with no obvious mechanism left to close the gap. The problem is that gravitational wave emission alone won't close it at that distance. At 1 parsec separation, two supermassive black holes would need approximately 10 billion years to radiate enough energy to merge. That's longer than the current age of the universe, so we have a real contradiction. Galaxy mergers happen constantly. We see their aftermath everywhere. Single massive black holes sitting in the cores of post-merger galaxies, merged, combined. The evidence that they do reach merger is undeniable. But if the final Parsec problem is real, how? Most astrophysicists now think it's not one answer, but a combination of several. Gas dynamics can help. In gas-rich mergers, the surrounding material forms a disk that pulls angular momentum away from the binary, nudging the black holes closer together. Stellar scattering is more effective than early models suggested, once you account for the messiness of real asymmetric galaxies. And sometimes a third galaxy falls into the mix. A third black hole joins the pair. The three-body chaos ejects one of them, and the remaining two are thrown into a tight enough orbit to finally merge. Nature finds a way, usually more than one way. The evidence that supermassive black holes do merge is overwhelming, but actually catching them in the act, two of them in a tight binary, separated by fractions of a parsec, weeks or months from their final collision, seemed nearly impossible. At those distances, at those separations, no optical or radio telescope on Earth can resolve them. The closer they get, the shorter the wavelength of light you'd need, and no instrument we have gets close. You can't see them directly, but you can hear them. Einstein laid this out in 1915. Accelerating masses produce ripples in the fabric of space-time, gravitational waves. The math was clear. Actually detecting one seemed like it belonged in a physics thought experiment, not a lab. A century later, in 2015, LIGO did it. Two stellar mass black holes, roughly 30 solar masses each, had merged 1.3 billion light-years away. The wave that reached us stretched and compressed the entire Earth by less than 1,000th the diameter of a proton. LIGO caught it. That is one of the most technically remarkable achievements in the history of science, and it opened a completely new way of observing the universe. But here's the constraint. LIGO has 4-kilometer arms. It detects gravitational waves in the tens to hundreds of hertz range, the kind produced by stellar mass objects merging in a matter of seconds. Supermassive black holes are a completely different problem. Billions of times more massive, circling each other over years and decades. The waves they produce are in the nanohertz range, billions of times lower in frequency than anything LIGO can sense. To catch those, you'd need a detector roughly the size of the galaxy. Turns out, we already had one. We just didn't know it yet. Millisecond pulsars are neutron stars that spin hundreds of times per second, firing radio waves into space with every rotation. Some are so extraordinarily stable that their timing competes with atomic clocks. Astronomers have been monitoring arrays of these pulsars scattered across the galaxy, measuring the precise arrival time of each pulse at Earth. Think about what that means. If a gravitational wave moves through the galaxy, it subtly stretches and compresses distances, including the distance between Earth and those pulsars. Pulses arrive a tiny fraction of a second early or late, in a specific correlated pattern across the entire array at once. In June 2023, NANOGrav, the the North American Nanohertz Observatory for Gravitational Waves published 15 years of data, and what they announced hit the astrophysics community like a truck. There is a gravitational wave background, a constant hum everywhere, coming from all directions simultaneously. Not one event, not one source, a background noise filling the entire galaxy, the way the cosmic microwave background fills the universe, except this isn't electromagnetic, it's gravitational. The most likely explanation: millions of supermassive black hole binaries spread throughout the universe, all of them spiraling, all of them radiating gravitational waves, those waves accumulating over billions of years into one persistent hum that saturates everything. The galaxy is humming. It's been humming for longer than Earth has existed. We just finally got quiet enough to notice. And once you know that hum is there, the next question becomes obvious. Can we find an actual binary? Something we can watch directly, close enough, bright enough, to track before the merger happens? The answer is yes. We already have candidates. OJ287. It's a blazar, a supermassive black hole with a jet aimed almost directly at Earth, which makes it one of the brightest radio objects in the sky, despite being 3.5 billion light-years away. Astronomers have observations of OJ287 going back to 1888. Photographic plates first, then telescopes, then modern observatories. Over that century plus of data, a pattern surfaced. Every 12 years or so, it produces two enormous optical flares, separated by about a year. The explanation that fits the data: not one black hole, two. The primary weighs roughly 18 billion solar masses, one of the most massive black holes ever measured. The secondary, orbiting around it, carries about 150 million solar masses. Twice per orbit, the secondary punches through the primary's accretion disk. Two passes, two flares, every 12 years. This has been predicted and verified. In 2019, astronomers calculated that the next flare would arrive on July 31st. It showed up within 4 hours of that prediction. 4 hours after 130 years of data. OJ287 is basically a physics testbed. The secondary moves so fast in its orbit that it loses measurable energy through gravitational wave emission. The orbital period is shrinking, slowly but detectably, at a rate that matches Einstein's predictions to within 1%. These two are merging in roughly 10,000 years. That's just one system. PKS 2131-021 is a blazar whose radio output has pulsed in a near-perfect sinusoidal pattern across 45 years of observations. The cleanest explanation is a supermassive binary whose orbital motion swings the jet back and forth across our line of sight once per revolution, like a slow lighthouse. 3C66b shows core motion, suggesting a binary with an orbital period of roughly 1 year, which would make it one of the closest candidates to actual merger currently on any list. These systems are at different stages of their in-spiral. Some have millions of years left, some possibly far less, and within the next decade, we'll be watching differently. LISA, the Laser Interferometer Space Antenna, is a space-based gravitational wave observatory being built by the European Space Agency with NASA contributions. 3 spacecraft forming a triangle in space, separated by 2.5 million kilometers, connected by laser beams. Where LIGO is 4 kilometers across, LISA will span 2.5 million. LISA targets the millihertz frequency range, exactly where supermassive black hole mergers radiate. When it launches in the mid-2030s, astronomers expect it to detect tens of thousands of gravitational wave sources per year, including mergers happening at the very edge of the observable universe. We won't just find the echoes afterward, we'll watch it happen. This is what everything has been building toward. 2 black holes, each carrying billions of solar masses, separated by a distance measured in light hours, light minutes, moving at a substantial fraction of the speed of light. The space-time around them isn't just curved, it's folded, twisted back on itself in ways that have no clean analogy to anything in ordinary experience. Numerical relativity simulations model what this looks like. Rings within rings, background stars smeared into arcs, light bending around each event horizon and back on itself again. The accretion disks, gas and plasma at hundreds of millions of degrees, have long since merged into one continuous, chaotic structure, feeding both black holes simultaneously. X-rays pour out in jets that can briefly outshine every star in the surrounding galaxy combined. And then something happens that billions of years of slow inward spiral couldn't. The separation crosses below the innermost stable orbit of the combined system. At that threshold, there is no more orbit. The in-spiral that took billions of years ends in hours, sometimes days. The final plunge is not gradual. The gravitational wave burst produced at the moment of merger is the most powerful single astronomical event in the universe since the Big Bang. For a fraction of a second, the merging system radiates gravitational wave energy at a rate exceeding the combined light output of every star in the observable universe. Every star, all of them, simultaneously. More energy than that, in a wave of pure space-time distortion. After the merger, the 2 event horizons combine into one. But here's the part that doesn't get talked about enough. If the 2 black holes had different masses or different spin orientations, the gravitational waves produced during the merger aren't symmetric, slightly louder in one direction than another. That asymmetry generates a recoil, a kick, that physically pushes the newly merged black hole through its host galaxy. In extreme cases, that kick reaches thousands of kilometers per second, fast enough to eject the black hole from the galaxy entirely. The most powerful event in the universe, and the thing it produces might simply leave. Most of the time the kick is smaller. The black hole stays, sinks gradually back to the galactic center over millions of years, reforms its accretion disk. The host galaxy, battered and scarred by the merger, slowly settles into an elliptical shape, the original spiral structure torn apart and scattered beyond recovery. Sagittarius A star, our galactic center, is currently quiet. Its accretion rate is far below what would make it active the way a quasar is active. It flares occasionally, brief brightenings in X-ray and infrared lasting hours or days, but by supermassive black hole standards, it's dormant. Andromeda's central black hole is also quiet. In 4 to 5 billion years, those two galaxies merge. The two black holes begin their own long in-spiral. Their merger, if our models hold, takes another few billion years after that. When it finally happens, the gravitational wave burst will be detectable, in principle, from anywhere in the local group. No one will see it. The sun will have long since passed through its red giant phase. The solar system as we know it won't exist. That timeline is hard to sit with. These events don't fit inside a human lifetime. They don't fit inside a civilization's entire history, or the remaining lifespan of our solar system. Galaxy mergers and black hole collisions run on the clock of the universe itself. Everything we've ever built, every name anyone has ever remembered, fits inside a rounding error on these timescales. And yet, in the 2023 NANOGrav data, we're picking up the cumulative signal of all of it. Every supermassive binary that has ever spiraled toward merger, across all of cosmic time, billions of systems, billions of years, has contributed to a background hum that still saturates everything. That hum passes through Earth right now. Through you, right now. The universe has been broadcasting in a language that requires instruments spanning light years to even decode. We built those instruments anyway, and we're only beginning to understand what it's been saying. Two black holes, billions of solar masses, circling each other for 100 million years. The universe isn't in a hurry, but we're watching now. If this gave you that feeling, that quiet vertigo of realizing how much is already happening out there without any of us noticing, subscribe. Every video on this channel is built the same way. Real science, no shortcuts, no hype, just the universe, the way it actually works. The next one hits different. See you there.